right, next up, we're going to be doing kind of a word problem where the approach uses this new method that we covered, kind of our application level problem. Last class was Newton's law of cooling. Now we're going to be doing this brine mixture concentration type problem. And I've written it out here so that you wouldn't have to listen to me read a lot of words out loud. But we're going to let X be the amount of salt in a 300-gallon tank. And I've drawn that tank right here. And then we're going to say that you're adding brine at concentration 2 pounds per gallon at a rate 3 gallons per minute into this tank. And then at a rate 3 gallons per minute, whatever's inside the tank will leave it. So you're kind of like always running liquid through this tank. And the idea is that you add it at that concentration, 2 pounds per minute, and then it leaves at whatever concentration it is mixed inside the tank. And we're supposed to solve an initial value problem for the amount in the tank if there is initially 50 pounds of salt in a tank, and then determine how much salt will be in the tank after a very long time. So our first part here is that we're going to have to set up our initial value problem. So we're told that there are initially 50 pounds of salt in the tank. So X is the amount of salt in the tank, and we're going to say when we plug in time 0, we have 50 pounds of it. Oh, wow. Sorry, I was writing kind of up and down for a second, so hold on, let me fix that. Equals 50. And then the tricky part here is that we need to write our differential equation. So dx dt is the change in the amount of salt in the tank over time. And at its simplest, we know that the way things change would be that we add on whatever we put in, and we subtract whatever we take out. And then our input is this 2 pounds of salt per gallon at 3 gallons per minute. So that's just going to be 2 pounds per gallon at 3 gallons per minute. And I should erase that so it's not up there. And if we do like a quick unit check, what we've got is the gallons cancel out. And so we have just 2 times 3, 6 pounds per minute. And if X is pounds of salt and T is minutes, then the dx dt, the derivative, is going to be pounds per minute. So these units check out. And then what we take out is going to be that everything's leaving at that 3 gallons per minute. But we need to convert this to the amount of salt that there actually is. So the current concentration would be X over 300 pounds per gallon. And so looking just at the entire container, the concentration of what's leaving is X over 300. And we can unit check this. The gallons cancel out, and you're again left with pounds per minute. So what I'm actually going to do is just move our whole thing down a little bit so we can see it all in one place. So we've got that dx dt should just be equal to 6 minus x over 100 with x of 0 equal to 50. Now, if we want to answer that question of how much salt is in the tank after a long time, that's sort of like those questions you had in your homework. The limit as t goes to infinity of x of t is question mark. And you know that you can solve that sort of thing just by an equilibrium problem. So to get 0 equal to 6 minus x over 100, you need x equal to 6 times 100, so just 600 pounds is an equilibrium value. And if we do the check, we'll actually find that that's stable. So without even solving the differential equation, we can answer that second question. X goes to 600 as t goes to infinity. After a very long time, you'd expect there to be 600 pounds of salt in the tank. And we'll touch on that more when we actually get a solution to compare to. But just kind of to bring this back to what you already know how to do with this type of problem, you can just answer it using equilibrium values. So we're going to continue this problem right here. Can't spell continue today, but that's fine. So to solve, dx dt is equal to 6 minus x over 100. I'm going to rearrange it in that standard form. Dx dt plus x over 100 is equal to 6. Now I have this in that sort of dy dx plus p times y is equal to f. Is that form that we want to always look at this type of problem in. And so for us, we're going to have that p is equal to 1 over 100 and f is equal to 6. And what's important to remember is that what we used to call y is x and what we used to call x is t. I know that that changing in notation can be confusing. The reason we do it is because you all will probably be interacting with differential equations at the application level. That means that the notation is going to change over time. So that's why we try to work in these little application problems where you have to kind of change the notation around. So what we're going to do is we're going to go ahead with our steps to solve a separable equation now that we know what p and f are. So if we have p is equal to 1 over 100, I'm going to go ahead and say that the integral of p with respect to t, now that that's the thing that's in the bottom of our derivative, is just the integral of 1 over 100 with respect to t, so that's just t over 100. And so that means my integrating factor here is going to be e to the integral of, well, I'll do it on the next line so I'm not running into that. So e to the integral of p dt is just going to be e to the t over 100. And so I know that I can change my differential equation into the following form. I would have my d dt of e to the integral of p, so e to the t over 100, times my variable that I'm solving for, that's x here, I know that it changed, is equal to f times e to the integral of p, so 6e to the t over 100. And then I can just go ahead and integrate both sides. I'm going to write that in this line right here, just because it kind of cuts down on space. So I get e to the t over 100 times x is equal to 6 times 100, so 600 e to the t over 100. And you can check that to make sure that it's correct, plus a constant c. Or x is equal to 600 when I move the dividing by e to the t over 100. 600 plus c e to the minus t over 100. So this is kind of the same approach as before. And our initial condition is how we're going to solve for c. So the initial condition, oh, sorry if I covered the mic just now. So what we should have from our initial value problem is that x of 0 equals 50. So x of 0 equals 50 equals 600 plus c e to the minus 0 over 100. So 50 equals 600 plus c. So c is 600 subtracted from 50, so it's just minus 550. And so our solution is x equal to 600 minus 550 e to the minus t over 100. So that's going to tell you how much salt is in the tank after any amount of time t. Now, when we come back into the next video, because we're running up against the time limit here, I'm going to go ahead and touch back on that question right here, how much salt is in the tank after a long time, differently than we did before.